If you give me about 45 minutes of your time, I will show you how to code a fully functional asynchronous advantage actor-critic agent in the PyTorch framework starting from scratch. We're going to have about 10 to 15 minutes of lecture followed by an about 30-minute interactive coding tutorial. Let's get started. Really quick, if you're the type of person that likes to read content, I have an associated blog post where I'm going to go into much more detail. Check the link in the description. Deep reinforcement learning really exploded in 2015 with the development of the deep Q-learning algorithm. One of the main innovations in this algorithm that helped it to achieve such popularity is the use of a replay buffer. The replay buffer solves a very fundamental problem in deep reinforcement learning, and that problem is that neural networks tend to produce garbage output when their inputs are correlated. What could be more correlated than an agent playing a game where each time step depends on the one taken immediately before it? These correlations cause the agent to exhibit very strange behaviors where it will know how to play the game and suddenly forget when it encounters some new set of states it has never seen before. The neural network really isn't able to generalize from previously seen states to unseen states due to the complexity of the parameter space of the underlying problems. The replay buffer fixes this problem by allowing the agent to randomly sample agents from many different episodes. This guarantees that those time steps taken are totally uncorrelated, and so the agent gets a broad sampling of parameter space and is therefore able to learn a more robust policy with respect to new inputs. As I've shown before on this channel, problems arise when you attempt to simply bolt on a replay buffer onto the actor-critic algorithm. It doesn't really seem to work, and in fact it's not very robust. Actor-critic methods in particular suffer from being especially brittle, and so adding on a replay buffer really doesn't help to address that problem. In 2016, a group of researchers managed to solve this problem using something called asynchronous deep reinforcement learning. It's a totally different paradigm for approaching the deep reinforcement learning problem, and in fact the technology can be applied to a wide variety of algorithms. In the original paper they detail solutions for deep Q-learning, n-step Q-learning as well as SARSA, and actor-critic methods as well. So what is this big innovation? Well, instead of having a replay buffer, we're going to allow a large number of agents to play independently on totally separate and self-contained environments. Each of these environments will live on a CPU thread, in contrast to a GPU for most deep Q-learning applications. This has the additional benefit that if we don't use a replay buffer, we don't have to store a million transitions, which for trivial environments really doesn't matter, but if you're dealing with something like, say, the Atari library, a million transitions can take up a significant amount of RAM, which can be a limiting factor for enthusiasts. So having the agent play a bunch of different games in parallel on separate environments, only keeping track of a small number of transitions, vastly reduces the memory footprint required for deep reinforcement learning. So in what sense exactly is this algorithm asynchronous? What this means exactly in this context is that we're going to have a large number of parallel CPU threads with agents playing in their own environments. They're going to be acting at the same time, but at various times they're going to be deciding what to do as well as updating their deep neural network parameters. And so we're not going to have any one agent sitting around waiting on another agent to finish playing the game to update its own set of deep neural network parameters. Each one will be totally independent and learning on its own. Now, we're not going to be simply throwing away the learning from each agent after it finishes the episode. Rather, we're going to be updating the network parameters of some global optimizer as well as some global actor-critic agent. So we have one actor-critic agent that sits atop all of the others, and the local agents that do all the learning by interacting with their environments. So what is the advantage part of A3C? So the advantage essentially means what is the relative advantage of one state over another. It stands to reason that an agent can maximize its total score over time by seeking out those states which are most advantageous or have the highest expected future return. The paper gives a relatively straightforward calculation for this. All we have to do is take the discounted sum of the rewards received over some fixed length trajectory and then add on an appropriately discounted value estimate for the final state the agent saw in that trajectory. Please note that this could be some fixed number like say 5 steps, or it could be 3 steps if the agent encountered a terminal state along the way. We're then going to go ahead and subtract off the agent's estimate of the value of whatever current time step it's in the trajectory. So that way we're always taking the value of the next state minus the current state. That's what gives us the relative advantage. So what does the actor-critic portion of A3C mean? Specifically, this refers to a class of algorithms that use 2 separate neural networks to do 2 separate things. So the actor network is responsible for telling the agent how to act, kind of a clever name, right? It does this by approximating a mathematical function known as the policy. The policy is just the probability of selecting any of the available actions for the agent given it's in some state. And so for a discrete action space, it's going to be a relative probability of selecting one action over another. So in our cart pull, it's going to be, say, 60% move left, 40% move right, so on and so forth. We're going to facilitate this by having two separate networks. The actor network will take a state or set of states as input and output a softmax probability distribution that we're going to be feeding into a categorical distribution from the PyTorch framework. We can then sample that categorical distribution to get the actual action for our agent, and we can also use that to calculate the log of the probability of selecting that action according to the distribution, probability distribution, and we will use that for the update rule for our actor. Now the critic has a little bit of a different role. The critic essentially criticizes what the actor did. It said, you know, that action you took gave us a pretty lousy state that doesn't have a very large expected future return, and so we shouldn't really try to take that action given that state any other time that we encounter it. So the critic essentially criticizes what the actor does, and the two kind of play off of each other to access more and more advantageous states over time. Before we go ahead and talk about the specifics of each class, let's get some idea of the general structure and flow of the program. The basic idea is that we're going to have some global optimizer and global actor critic agent that sits on top that keeps track of everything the local agents learn in their own individual threads. Each agent will get its own specific thread where it can interact with its own totally distinct and separate environment. The agent will play either some fixed number of time steps or until it encounters a terminal state, at which point it will perform the loss calculation to do the gradient descent on the global optimizer. Once it calculates those gradients, it's going to upload it to the global optimizer and then re-download the parameters from that global optimizer. Now keep in mind, each agent is going to be doing this asynchronously, so while one agent is performing its loss calculations, another agent may have already finished that loss calculation and updated the global optimizer. That's why right after calculating the gradients, we want to go ahead and download the global parameters from the global actor critic, so that way we make sure we are always operating with the most up-to-date parameters. After each time the agent performs an update to its deep neural network, we're going to want to go ahead and zero out its memory so that it can start fresh for another sequence of 5 or until it encounters a terminal state number of steps. So now let's talk implementation details. We're going to have a few separate distinct classes for this. The first of which is going to be overriding the Atom optimizer from the base PyTorch package. So we're going to have a shared Atom class that derives from the base Torch Optim Atom class, and this will have the simple functionality of telling PyTorch that we want to share the parameters of a global optimizer among a pool of threads. It's only going to be a few lines long, and it's much easier than it sounds, and I'll show you how to do it in code. Our next class will be the actor critic network. Now, typically we would use shared input layers between an actor and a critic, where we simply have one input layer and two outputs corresponding to the probability distribution pi and the value network v. But in this case, we're going to host two totally separate distinct networks within one class. It's a relatively simple problem, the cart pull, and so we're going to be able to get away with this. The reason I'm doing it this way is because I frankly could not get shared input layers to work with the PyTorch multiprocessing framework. Our agent will also have a memory, which we're just going to use simple lists for that. We're going to append states, actions, and rewards to those lists, and then go ahead and set those lists back to empty lists when we need to clear the agent's memory. We're going to have a function for calculating the returns, where we're going to use the calculation according to the algorithm presented within the paper. So the idea is that we're going to start at the terminal step or the final step in the trajectory. If that step is terminal, the R or the return gets set to 0. If it's not, it gets set to the current estimate of the value of that particular state. Then we're going to work backward from the t-1 time step all the way to the beginning, and we're going to update R as R sub I plus gamma times the previous value of R. Now I'm going to do a calculation in the video, the coding portion, to show you that these two are equivalent, meaning this calculation as well as the earlier advantage description I gave you. I'm going to make sure that you understand that those are actually equivalent, and it's just a few lines of mathematics, so it's not really that difficult, and I've taken the liberty of doing it for you. Then we're going to be calculating the loss functions, and these will be done according to the loss functions given in the paper. So for our critic, we're going to be taking the delta between those returns and the values and taking the mean squared error. For our actor, we're going to be taking the log prob of the policy and multiplying it by the advantage and with a -1 factor thrown in there as well. Now that's a really cool way of calculating the loss for the actor because it has a pretty neat property. So when we multiply the advantage by the log of the probability, what we're actually doing is weighting probabilities according to the advantage they produce. So actions that produce a high advantage are going to get naturally weighted higher and higher over time, and so we're going to naturally evolve our policy towards being better over time, which is precisely what we want, right? Our final class will be the agent class, and this will derive from the multiprocessing process subclass. So here's where all of the real main type functionality is going to happen. So we're going to be passing in our global optimizer as well as our global actor critic agent, instantiating 16 in the case of 16 threads for a CPU, local critics with 16 separate environments, and then each one of those is going to have 2 separate loops where it's going to go up until the number of episodes that we dictate, and it's going to play each episode. As I described earlier, within each episode it's going to play some fixed sequence number of steps, and then it is going to perform some update to the global optimizer and then download the parameters from the global actor critic agent. Our main loop is basically going to set everything up. We're going to go ahead and define all of our parameters, create our global actor critic, our global optimizer, and tell PyTorch that we want to share the memory for our global actor critic agent. And then we're going to make a list of workers or agents, and then we're going to go ahead and send each of those a start command as well as a join command so that we can get everything rocking and rolling. So what are some critiques of this algorithm overall? Well, one is that it is exceptionally brittle. Most actor critic methods require a fair amount of hyperparameter tuning, and this one is no exception. I tried to use the lunar lander environment but couldn't really get a good set of parameters to make it run effectively and get a consistent score of 200 or above, or heck, even a consistent score of over 100. I would have called that good enough for YouTube. Another one is that there is a significant amount of run-to-run variation, so it's highly sensitive to initial parameters. You can solve this by setting global seeds for the random number generators so that you're getting consistent random numbers over time, and so you're going to know exactly how you're starting. But to me, it's a little bit kind of like cheating, so I don't do it in this video, but it is something to take note of. And in the original paper, I think they do something like 50 different runs of each evaluation, some large number to get a pretty solid distribution of scores. And that is, I think, because of the high degree of run-to-run variation. Okay, I have lectured at you enough. Again, if you like to read written content, I have a link in the description to a blog post where I talk about this in a little bit more detail. But nonetheless, let's go ahead and jump right into the coding tutorial. Let's go ahead and start with our imports. We will need Gym for our environment. We'll need our base Torch package. We'll need Torch multiprocessing to handle all of the multiprocessing type stuff. We will need Torch NN to handle our layers. We'll need NN functional to handle our activation functions. And we're going to need our distribution as well. And in this case, we're going to need a categorical distribution. All this does is takes a probability output from a deep neural network, maps it to a distribution so that you can do some actual sampling to get the real actions for your agent. Now, I want to start with the shared atom class. This will handle the fact that we are going to be sharing a single optimizer among all of our different agents that interact with separate environments. All we're going to do here is call the base atom initializer and then iterate over the parameters in our parameter groups, setting the steps exponential average and exponential average squared to zeros effectively, and then telling it to share those parameters amongst the different pools in our multi-threading pool. And this will derive from the base atom class. Our default values are going to be, I believe, identical to the defaults for the atom class. And then we want to call our superconstructor. Now we're going to handle setting our initial values. And then we're going to tell Torch that we want to share the memory for our parameters, or for our gradient descent. And note the presence of the underscore at the end of memory there. Okay, that is it for the shared atom. Pretty straightforward. Next up, we want to handle the actor-critic network, which will also encapsulate a lot of the functionality I would typically put into an agent class because of my understanding of the design principles of object-oriented software programming. In this case, I have to shimmy a few things around because the agent class is going to handle the multiprocessing elements of our problem, and so it doesn't really make sense to stick this like the choose action memory functionality in the agent class. So we're going to stick it in the network class. It's not a huge deal, it's just a departure from how I normally do things, and certainly not everybody does things the same way I do. So our initializer takes input dims from our environment, number of actions from our agent, and a default value for gamma of 0.99. We also have to save our gamma, and the next thing we want to handle is writing our actual deep neural network. Now, this is also a little bit different than the way I normally do things. Normally, I would have a shared input layer that branches out into a policy and a value network as two separate outputs with that shared input layer. When I tried to do that, I found that the software doesn't actually run. It doesn't handle the threading aspect very well in that case when you have shared input layers from a deep neural network. I don't know exactly why that is. If you know, please leave a comment down below because I'd be very curious to hear the explanation. It's simply what I found out through my own experimentation. So we're going to have two separate inputs, one for the policy and one for the value network, as well as two separate outputs. So they're effectively two distinct networks within one single class. And we're only going to be using 128 neurons here, not a very large network. And our output will take those 128 hidden neurons and convert it into number of actions, and our value function will take likewise the 128 hidden elements and convert it to a single value, or if you pass in a batch of states, a batch of values. The agent also, the network also has some basic memory, so rewards, actions, and states. These we will handle just by appending stuff to a list, and each time we call the learning function, we're going to want to reset that memory. So let's go ahead and handle that functionality first. So the remember just appends a state, action, reward to the relevant list. And a clear memory function just zeroes out all those lists. Pretty straightforward. Next we have our feedforward function. That takes a state as input. So we're going to pass that state through our first input layer for our policy and perform a ReLU activation on that, and do something similar for the value input layer. And And the outputs of those two are going to be passed to the relevant policy and value outputs. And then we just return pi and v. Pretty straightforward yet again. Next, we're going to have our function to calculate the returns from our sequence of steps. So this will only take a single input, and that will be the terminal flag. Recall that the return for the terminal step is identically 0, so we need the terminal flag or the done flag to accommodate that. So we want to go ahead and convert the states from our memory to a torch tensor of t.float data type, because it is a little particular about the data type. You don't want to pass it in double, it gives you an error, so best to take care of it now. We're going to go ahead and pass that through our neural network, and we're not going to be concerned with the policy output at this stage. We just want to know what the value evaluations the critic has for that set of states. So our return is going to start out as the last element of that list, so the terminal step or the last step in the sequence of steps, and we're going to multiply that by 1 minus int done, so that if the episode is over, 1 minus done is 0, so you're multiplying by 0, you get 0. Pretty handy way of handling that. Then we're going to handle the calculation of the returns at all the other time steps. So we're going to go ahead and iterate over the reversed memory and say that our return is the reward at that time step plus gamma times r, and then just return, append that return to the list of batch returns. And then finally at the end, you want to go ahead and reverse that list again so that it's in the same order in which you encountered the states. This calculation reverses it because you're starting at the end when you know the value of the final state, or at least the estimate of the value according to the critic, and then reversing it to get it back in order for passing it into our loss calculation function. Now this may be a strange form to you. If you write it out by hand, maybe I can show you something here where I did it for you. If you write it out by hand, this particular chunk of code, you can see that it's identical to what they tell you the calculation is in the paper. So yeah, you can do that exercise on your own to convince yourself, or I can just show it to you so that I can convince you of it. But this is indeed the return calculation from the paper. Everything is as it should be. And then I want to convert that to a tensor and return it. Next, we have to handle the calculation of our loss function, and this again is only a single input, the terminal flag from the environment. We're going to go ahead and get the value, the tensor representations of our states and actions right at the beginning. And then we're going to go ahead and calculate our returns. And then we're going to perform the updates. So we're going to be passing the states through our actor critic network to get the new values, as well as then a distribution according to the current values of our deep neural network. We're going to use that distribution to get the log probs of the actions the agent actually took at the time it took them. And then we're going to use those quantities for our loss functions. Values squeeze. Now this squeeze is very important. If you don't squeeze here, it won't trigger an error, but it will give you the wrong answer. The reason it will do that is because the actor loss and the critic loss, I believe, will come out as shape 5 by 5. And that is not the shape we want. We want something, in the case of 5 time steps, T max equals 5. So it'll give you a 5 by 5 matrix instead of a 5 element vector. So you have to perform the squeeze here to get the 5 by 1 output of the deep neural network into something that is just 5, a list of 5 elements, or a vector of 5 elements instead of 5 by 1. So definitely need that squeeze. If you don't believe me, by all means, erase the line, or comment it out and print out the shapes of things to the terminal. I always recommend doing that. It's a good way of solidifying your understanding of how all this stuff works. So then our critic loss is just the returns minus values squared. Pretty straightforward. So now let's go ahead and say that we want the softmax activation of our output, and that has a property that, of course, the softmax guarantees that every action has a finite value, and that the probabilities add up to 1, as all probability distributions should. So then we use that output to create a categorical distribution and calculate the log probability distribution of our actions actually taken. Then our actor loss minus log probs times the quantity returns minus values. That's from the paper. And then our total loss is just critic loss plus actor loss dot mean. And we have to sum the two together because of the way that the backpropagation is handled by PyTorch. And of course, I did forget the choose action function, but that is not a big deal. We'll just go ahead and handle that now. So that will take, we're going to call it observation as input, because we're going to be passing in the raw observation from our environment. And so we have to convert that to a tensor right off the bat, and we have to add a batch dimension to that for compatibility with the inputs of our deep neural network. And we're going to call it a D type of float. We pass that through our neural network, get our policy and value function out, perform a softmax activation on our policy along the first dimension. Then we're going to create our distribution based on those probabilities and sample it and convert it to a NumPy quantity, take the 0th element and return it. So that is it for our actor network class. It encapsulates most of the functionality I would associate with the agent, but it does everything we're going to need each of the independent actors within their own thread to do. Now we're going to move on to the agent class that is going to handle our multiprocessing functionality. So I'm going to call this agent. You will sometimes see it referred to as worker, and that is a fine name. That is kind of precisely what it is. I'm just using agent to be consistent with my previous nomenclature. It has to derive from the mp.process class, so we get some access to some goodies there. So we will need our global actor critic. That is what is going to handle the functionality of keeping track of all the learning from all of our environment-specific agents. The optimizer, that is going to be the shared atom optimizer that we wrote earlier. Input dims, number of actions, gamma in case you want to use something other than 0.99, a learning rate, a name to keep track of each of the workers from our multiprocessing, the global episode index. So this will keep track of the total number of episodes run by all of our agents. It's not as easy as of a concept as it may seem, because you're doing asynchronous processing, as well as an environment ID. So the first thing I'm going to do is call our superconstructor and go ahead and start saving stuff. So our local actor critic is just going to be our a new actor critic with inputs of input dims, number of actions, and gamma. We want to save our global actor critic so that we can update its parameters. We're going to have a name for each worker in its own independent thread, and that's just going to be just worker number name. And then we'll have an episode index, global episode IDX, our environment, So environment ID is a string here, if that isn't clear. And our optimizer. Did I spell that correctly? Yes, I believe I did. So we have to define a very specific function so that stuff actually works. And that function is the run function. This gets called behind the scenes by the worker.start function that we're going to handle in the main loop. But this handles effectively all the main loop type functionality of our problem. So our global time step is going to get set to 1, while our episode idx.value, so episode idx is a global parameter from the multiprocessing class, and that we want to get the value by using the .value dereference. And while that's less the number of games, some global variable we're going to define. In other words, while we have not completed all of our games, set your terminal flag to false, reset your environment, and set the score to 0, and go ahead and clear the agent's memory at the top of every episode. And then while you're not done, so go ahead and play your sequence of episodes, sequence of steps within an episode. The action is chosen by your local actor critic. So you're going to pass the observation into each local actor critic. So each of these 16, in this case, threads will get its own local actor critic, and that'll synchronize to the global. But you never actually use the global network directly to do things like choosing actions. So get the new state reward done and debug info back from your environment. Keep track of the reward received as part of the total score. Remember that observation, action, and reward. Then we have to say if the number of steps modulus the maximum number of steps is 0. In other words, if it is every 5th time step, or we have finished the episode with that last time step, then we're going to go ahead and perform our learning step. Modulus t max. Or we're done. Then we're going to go ahead and handle the learning functionality. So we'll say loss equals local actor critic.calc loss. And of course, we need the most recent terminal flag as the parameter for that function, the argument. Go ahead and 0 your gradient and back propagate your loss. So we're going to set the parameter for the global gradient to the local agent's gradient at this step. And then after doing that, we can tell our optimizer to step. And then we can go ahead and synchronize our networks. And we do that by loading the state dictionary from our global actor critic to our local one. And then we want to go ahead and clear the memory after each learning step, and then tell the algorithm to increment t step by 1, the global time step, and set the current state to the new state. Then at the end of every episode, we have to handle the fact that we may have finished an episode from another agent while one thread was running, because this is running asynchronously. So we say with self.episode idx .getLock, so we want to make sure that no other thread is trying to access that variable right now. And if we can, go ahead and increment that episode value by 1. Then we do the usual print the debug stuff to the terminal. We're going to print out the name of the worker, the episode, and that is self episode IDX value, and the reward, the total score from the episode. And that is it for our agent class. So this is relatively straightforward. All we're doing is handling the fact that we have our local parameter, our local agent that chooses actions. We're going to perform the gradient descent optimizer update using the gradients calculated by the actions of that agent, and then upload that to our global network so that every agent uploads its learnings to the global network, and then we're going to go ahead and download that from our global network as well, so that we make each agent in its own thread better over time. Now we have our main loop, and we're going to do some stuff like declaring our learning rate, our environment ID, cart poll v0. Number of actions for that environment is just 2, left and right. Input dims is just a 4 vector. We'll say number of games 5,000. You know, we can actually get away with 3,000, I believe. T max every 5 steps. That comes from the paper. Our global actor critic gets initialized here, and that takes input dims and number of actions. We want to tell that global actor critic object that we want to share its memory. Then we have our optimizer. What are we going to be optimizing and sharing? The parameters of our global actor critic network. Learning rate defined by learning rate, and betas 0.92, 0.999. I get that from Morvan Joe's stuff. I haven't experimented with that too much. A little bit of cargo cult programming here. I apologize for that. Now we have our global episode, and that is just going to be a value of type I. That means unsigned integer. Doesn't mean I as an counter variable. You could also have D for a double if you wanted to keep track of like a score or something like that. I just means unsigned integer, or no, it's a signed integer, so it can be negative as well as positive. Now we have to create a list of workers, and that's going to be a list of our agents. And this is the construct that we're going to use to handle the starting and running of our specific threads. So that's an agent. We have to pass in our global actor critic, our optimizer, our input dims, number of actions, a gamma, a learning rate. It's helpful to use commas. Our name is just going to be the name is just going to be the I in our list comprehension. Our global episode IDX is going to be that global EP variable we just defined, and we're going to pass in our environment ID for I in range multiprocessing.cpu count. Now I haven't noticed a huge difference in running this with different numbers, so something other than CPU count in the range. I have 16 threads. If I tell it 8, it still uses all 16, so I'm probably missing something here. I could do a deeper dive into the documentation to figure it out, but for the purposes of the video, I'm just going to go ahead and roll with it. So now we want to go ahead and start all of our workers, and then go ahead and do our join operation. Okay, so now moment of truth. I want to find out how many typos I made in the recording of this. Let's go ahead and do a right quit. I already have an invalid syntax, so I say for reward in. That's an easy one. no others. So let's say A3C.py. Okay, name env is not defined. That's because it is self.env. So that is in line 114. Self.env reset. Cannot assign torch float tensors child module pi1. Torch NN module or none expected. So that is when I handle the feed forward in our choose action function. Ooh, this is an interesting one. I haven't encountered this before. Let's take a look. Cannot assign as child module pi1. Oh, that's because, interesting. Oh, of course. Yeah. Obviously, I don't want that self here. I'll have to annotate that when I am editing the video. That is obviously going to be problematic. So you'll probably have seen that already, that I put in a no self dot in there. Okay. That's the beauty of doing things for... oh, it's because it's log prob, not log probs. That's in 85. Log prob. I hope I remember all these. Has none type object, has no attribute backward. I probably forgot to return my loss. Yeah, that's right. There we go. All right, now it's running. Hopefully it's still going to record even though it is running across all of our threads. Looks like we're still good. Now you see that executed really, really fast. It was so fast I didn't even have time to get up the thread count, the resource monitor to show you guys. But you can see here that it achieves a non-negligible score, so that indicates some learning is going on. Now let's go ahead and run it again, and you can see now this time it's not doing any learning at all. So there is a significant amount of run-to-run variation. So I'll let it run and finish, and we'll try one more time, and maybe we'll get lucky and it will actually approach a score of 200. Nope. That's one of my big criticisms of this algorithm, is that there is a significant amount of run-to-run variation, and it is pretty brittle with respect to some other algorithms that came later. Basically, the main advantage here is that it's asynchronous, and this paradigm can be employed on many different types of algorithms, as you read in the paper. You know, it can be applied to deep Q learning as well as n-step learn, SARSA, stuff like that. Okay, so it's getting a little closer. Okay, so this one took a little bit longer because the episodes actually achieved scores of 200, which is the max. Not every thread manages to be a winner. Not all of us can be winners in life. That's a nice little microcosm of the universe. But you can see that for the most part, some of the workers... Actually, I wonder if there was consistency amongst... So worker 11 got 200. And if I scan down here, another worker 11, 142... 161. Interesting. So you do get actual learning across your agents. It's just not super consistent, and that is my biggest criticism of this algorithm, is that it has a high degree of run-to-run variation, as you can see, but it's still pretty good. It's an interesting take on deep reinforcement learning, and I do enjoy the algorithm. It's just not what I would categorize as the top 2 or 3 algorithm in actor critic methods. I hope this was illustrative for you. I hope you found it very helpful. If you have made it this far, please consider subscribing, leave a like, a comment down below, and I'll see you in the next video.